Okay, let's jump in. We all know solar energy is, well, absolutely essential for our renewable future, right? It's powerful, clean. But there's always been this issue, heat.
Heat is a major limitation.
The hotter a panel gets, the less efficient it is, and it degrades faster, too.
Exactly. Performance drops, lifespan shortens.
We've been looking at this really interesting article about an invention out of KAUST King Abdullah, University of Science and Technology. Look like they might have a novel way to tackle this heat problem.
Yeah, and it's a big deal because, standard cooling, it often uses energy itself.
Yeah.
Fans, pumps.
Right, kind of defeat the purpose a bit.
Precisely. So our mission today is to really dig into this source, see how this new material cools things down passively, no extra energy needed.
Okay, let's unpack that. The article calls it a composite material. What exactly is it made of?
So according to the research, it's an acrylic-based composite. The main ingredients are lithium chloride and sodium polyacrylate.
Okay.
And the key property is that it's hygroscopic.
Hygroscopic, meaning?
Meaning it absorbs moisture. Think of it like a sponge for water vapor in the air. It soaks it up at night, when it's cooler, more humid generally.
Good.
Then during the day, as the sun beats down and heats the panel, it releases that stored moisture back into the air as vapor.
And that creates a cooling effect.
Exactly. Evaporative cooling right there on the panel's surface. Passive, elegant, as you said.
That is clever.
Yeah.
And the results they reported, pretty striking numbers, right?
Oh, absolutely. The tests they ran, particularly in the Saudi desert conditions, showed panels with this material running, on average, 9.4 degrees Celsius cooler.
Wow, 9.4 degrees, that's significant.
It is. And that temperature drop led directly to a power output increase of 12.9%.
Nearly 13% more power just from staying cooler.
And maybe the most impressive part, long term. They projected it could extend the panel's operational lifespan by over 200%.
200%.
Yeah.
That changes the economics completely.
Right. They calculated it could cut the levelized cost of generating electricity, the overall cost over the lifetime, by almost 20%.
And it wasn't just tested in the desert, was it? I think the article mentioned other locations.
That's right. They tested it in the Saudi heat, yes, but also in cooler, even rainy conditions in the mainland U.S.
So it seems to work across different climates.
It suggests it does, yeah. And they used high-performance solar cells for testing, too, from Professor DeWolf's group, who are, real leaders in that field. Adds credibility.
And the material itself. You said sodium polyacrylate. Isn't that pretty common stuff?
Extremely common and inexpensive. It's the absorbent stuff in disposable diapers, actually.
Oh, no kidding.
Yeah. So we're not talking about some rare, expensive element. And the source mentions the fabrication process is straightforward, doesn't require harsh chemicals.
So potentially cost-effective to make it scale.
That seems to be the implication. It's fascinating how, relatively simple, accessible materials can lead to such significant results when engineered cleverly.
Yeah, the article frames it as a nice piece of collaborative work there at KAUST, right? Connecting material science with the practical needs of solar cell design.
Definitely.
So thinking about the bigger picture, what does this all potentially mean for you, the listener? Well, this research points towards solar panels that could be quite a bit more powerful, especially in hot weather.
And last much, much longer. Years longer.
Which, in turn, could make the electricity they produce cheaper over the panel's lifetime. And all this cooling happens passively without using extra energy.
Yeah, and if you zoom out even further, think about the global implications. If this material really is cheap to make and works well everywhere, deserts, tropics, temperate zones,
it could make solar power much more accessible, more reliable, pretty much anywhere in the world.
It really could boost adoption significantly. Which, well, it brings up an interesting question, doesn't it?
What stands out to you about the potential for these kinds of passive, materials-based solutions to sort of quietly revolutionize renewable energy going forward? Something to think about.